US Army Research Laboratory. And this work looks at using synthetic data for making AI systems more robust. So where does synthetic data give the most benefit? Where real data is expensive to acquire or unavailable, imbalanced. So you have one class with very rare data, or it's unusable because of privacy regulations. And the most common use cases are computer vision in health and privacy, and also for business. So in particular, we look at the problem of improving the robustness to unseen scenarios. So we use Unity, a game engine, to replicate the real scenes with these, and augment the data set with synthetic scenes, which have similar statistics. And then we have the data set, which consists of multiple orientations of the infrared vehicles. So the experiments that we do are to train the model on certain orientations of the vehicle and test it on different orientations of the vehicle. So we want to show that synthetic data can improve the robustness here to the unseen orientations. So we do a couple of experiments where we train on the real data on this set of orientations, so -20 to 20 degrees, and similarly the other way, so where the vehicles are coming towards us and going away from us. And then we augment the real data with synthetic data of these orientations that we are going to test it on. And we show an improvement of up to 20% in multiple metrics of MAP50, precision, and recall. So this way these are preliminary results for this work, but these are promising results. So so this is essentially, so we want to show synthetic data can improve robustness to unseen scenarios and also unseen classes, different data modalities, for example, electro-optical or infrared. And in particular, in general, we want to show that synthetic data has a use case for machine learning, and to make it more, the workflow of training AI more streamlined and robust. So here I'll hand over to Dan now. So yeah.
Okay, thank you very much, Nitish. So I'm also from the Turing Institute up in the British Library in London. So feel free to come visit us if ever you're in the area. So today I'm going to talk about neuromorphic hardware. Some people might have heard about that before, some people might maybe not, but hopefully by the end of the talk you'll have a good understanding of what neuromorphic hardware is and why we might need it for reasons of sustainability. So yes, neuromorphic hardware. We're basically going to be talking about neurons, biological neurons, a lot today, but we're going to avoid the sort of details of the sort of biomechanics going on. We're going to stay at a very high level because that's where I prefer as an electronic engineer. So why are we talking about biological neurons? Well, a lot of times when we want to use machine learning, we want to do them in scenarios where we're dealing with a very small physical space. We might need to operate with minimal power consumption because we might be, say, flying a drone, or we could have a biomedical device that we want implanted. We don't want to be charging it the whole time. But crucially, we need it to be adaptive. So we need some way of deploying ML in these quite constrained environments. And naturally, if the model is very large, if it requires a server rack, and if it consumes a lot of energy, it's not going to be fitting in these applications. So in order to try and find a solution to this problem, we're going to start by looking at AlphaGo, which I'm sure many of us have heard about. It was an ML agent developed by DeepMind, branch of Google, that basically plays the game Go, and infamously has beaten all of the world's top Go players. So to get an idea of the sort of theme of this talk, we're going to look at a table in the publication that summarizes how well this ML agent was performing. And that's shown on the far right column here, the ELO score. Basically, if that score's higher, the game better. And we're going to look, as we work down this table, we can see the score of AlphaGo getting better and better. But it's not until we get to the bottom half of this table that we suddenly have a large jump. And we go from a performance of in sort of the high 2000s, all of a sudden we're in sort of the low 3000s. And this is quite a non-linear function is score, right? So if we get a jump like that, it's pretty impressive. So how was that achievement achieved? Well, that answer is sort of given away in these two columns here, when we look at the hardware that was used in those scenarios. So we've got a table listing the CPUs and also the GPUs. And we can see that jump in performance corresponding to almost a 10 times increase in the hardware being used. Right, we've gone from 48 CPUs up to 428, also almost up to 2000. Similar story when it comes to the GPUs. Now, the problem is that's causing a problem, and Romain has sort of summarized that today perfectly, so I'm not going to spend too long on this. But what this leads to is a massive increase in compute requirements. So what we're looking on the x-axis here is sort of, as we're scrolling through time. On the y-axis, we're looking at the amount of petaflop days that it took to train some sort of iconic models. So you can see on the top right here, GPT-3, which obviously is now a bit outdated. But what this graph is telling us is that these sort of massive, impressive feats in machine learning performance has corresponded to also an increase in compute resources. What's even more scary is that this is not a linear graph. This is an exponential graph, suggesting an exponential increase in compute requirements. We know that kind of growth is not sustainable. So the question is, how are we going to change that? Also, this naturally has implications for environment. So the nice study here cited Ed of Struble looking at CO2 production, and they found one NLP model was producing similar amounts of CO2 as 7 years as an average human life would. But maybe we shouldn't use CO2 as a metric, as citing earlier. So how do we solve this problem? Well, we're going to go back to AlphaGo, because we can also see a suggestion of a solution to that problem in AlphaGo's work. So what we're looking at on the table here is AlphaGo and its sort of power consumption in it playing a few different games. So playing Fan, which is basically the game before the big movie that maybe some of you have seen, and then Lisa Lell here is the subject of the movie. And we can see quite a drastic jump or reduction in power consumption. So the question is, what's caused that? How did they achieve that? And they actually continued even further, which is pretty impressive. Well, the answer to that is kind of hidden away in this x-axis here, where we've gone from using 176 GPUs to 48 TPUs. Well, what is that? It's a change in hardware to this bit of kit here, which is a TPU, and it's essentially a bit of hardware that's optimized for carrying out sort of matrix operations that's used in machine learning. And this is a natural flow. GPUs were developed to optimize graphics and drawing graphics. TPUs are sort of another building upon that to focus on matrix operation. So there's a general trend then that wants to reduce the compute requirements of ML systems to change the hardware. And that's where you're going to get these big jumps in reductions. So that brings us on to the topic of today, which is neuromorphic computing. Because if you look at the power consumption of today's ML agents, compare that to the amount of power that you're consuming, so your human brain is roughly consuming very to have some kind of parameter. Point number two.
Nah, you probably won't.
I think it's safe.
Okay, is that better?
Yeah.
Okay, cool. So if we want to replicate neurons, one of the key things to replicate is the way neurons encode information. And it seems, again, a lot of this we aren't entirely sure on, but the best guess is that neurons encode information in these sort of spike waveforms that they produce. So if you watch a neuron, often it might not be doing something that much. There's a lot of space. And then all of a sudden you get this sort of pulse in the potential between the inside of the neuron and the outside. And we think that's how information is transferred within the brain. Now, this is quite cool from reducing power perspective, because, as I said, a few seconds ago, neurons are often quiet. They're not doing anything for a lot of the time, which from a power perspective is quite attractive, because if you can have your computer not computing when you have very little inputs, that's quite useful, right? We're not triggering transistors or consuming that you have. So we're going to do a very quick whistle-stop tour of neuromorphic engineering. So we're not going to go into too much of the details, but the question is, can we replicate that kind of behavior? The answer is yes. It's been done for a long time, actually. So this is one example of an architecture by a researcher who's quite big in the field, Giacomo Diveri in Surrey. And you can see, yes, bottom right-hand side is recordings from biological neurons, and then recordings from the bottom here are from actual that circuit that you can see at the top. Now, what's quite nice is you can see quite a few behaviors in both the biological and the artificial. We can see sort of this bursting behavior, which we see here and here. We can see we get low frequencies here, and we can also increase the frequencies here. So these circuits are great. They basically allow you to produce a lot of neural behaviors. But we can't rely just on neurons. We also need to build the connections. And we build neural networks. We know what these connections are called. They're synapses, and we know what they do. They're there to sort of weight signals. In neuromorphic engineering, we often treat synapses a bit differently. We like to use these online learning rules where maybe you don't use backpropagation, but you have some kind of policy that updates the weights in real time. And that's based on some rules that you often see or you can detect in actual biological samples. The advantage of that is that the weights update without you having to sort of have access to the weights. And if you're actually going to be physically building these neural networks, you kind of need that, because it's unlikely that you're going to be able to get wires into every single weight within the neural network. So can you build them? Yes, you can. This is a nice little circuit that shows you one of those. But people try not to take this approach to building synapses. Synapses are very small interconnections. They're very populous, they're very dense. So we cannot rely on building synapses using conventional electronics, because they just take up too much space. So people also looked at other ways of building synapses based on material science. So if you look at the structure of the synapse, you have sort of your conductive element at the top, then you have a sort of insulating kind of layer, and then another conducting element. What does that sound like? If you go back to sort of our A-level physics, it sounds like a capacitor. Yeah. Only thing is, it's quite a bad capacitor in that you are allowing current to flow through in certain conditions. But it turns out you can actually build these from taking a metal, deposit some silicon dioxide, which is an insulator, put another metal on top, and you can reproduce really similar behaviors that you see in biology. So here is, I think, biological recordings of how synapses change over time, and here is it might be hafnium dioxide, I can't remember the exact material. But we won't go into details just for time's sake. But essentially, shape is saying, so good, we can build synapses. So the question is, we can build neurons, we can build synapses. So what? If people actually build chips that try to operate in a sort of spike-based neuromorphic way. And yes, and it's been quite successful. So we can see a range of chips here dating back to a while to actually more recent chips from university spin-outs, fabs from IMEC, Spinnaker based in Manchester. It's a sort of a distributed compute version. And Intel are really pushing these kind of areas in spiking neural networks. They have their Loihi chip. They've recently brought out the sort of server rack version. And if you want to, with loads of neurons, you can play around with. Question is though, are they any good? Do they actually reduce the power consumption? Let's find out. So this is quite an old benchmarking paper, I think from 2016. So not on that optimized hardware. So what IBM did is they took their True North neuromorphic chip and they applied it to keyword spotting and image recognition. And they did this for accuracy and, so they computed the accuracy and also the power consumption. And this is quite an important point because what they found was, in general, we had worse accuracy. There's a little bit of a reduction. But that's okay because they were able to compute on a power consumption of 25 milliwatts to 275 milliwatts. Right, that's a pretty good power consumption for a model that's on hardware that hasn't really been optimized. And they were classifying at a rate of 1,200 to 2,600 per second. So suggesting you could do video with that tool as well. Intel also benchmarks their Loihi chip in keyword spotting exercises, and they found their chip was 100 times more power efficient than GPUs, which is quite impressive in that same task. But we have to be careful because if you dig a bit deeper into the hardware, into the paper, you do find that we're reducing the amount of energy. So this table kind of summarizes energy consumption in sort of the ideal running and dynamic states. And what's interesting, the neuromorphic chip, as we explained earlier, when it's at rest, it really has a sort of reduced power consumption compared to the other two, because when it's at rest, there's no spike, there is no sort of events, so there's no power consumption. So in all three categories, you can see a real reduction in power, which is great. That was what was promised. But it's a lot slower to infer. So you have to run the thing for a lot longer. So they also looked at the performance metric of your sort of energy consumption per inference, which takes into account how long that inference took. And then you found that, yes, it's still an improvement, but not quite as dramatic as it originally looked like it was. But I would take that with a pinch of salt because obviously these are quite, new ideas, new chips. They haven't had the same level of optimization that GPUs and CPUs. So that brings us to the end of the talk. So neuromorphic engineering, the aim is basically, can we try and build computers that replicate the human brain so we can reproduce the power efficiency of the human brain? It does face some challenges though. So key thing in neuromorphic engineering is that you actually build the networks rather than them being stored in memory. Because of that, it's very hard to change the structure. If you want to change the number of layers or add new neurons, you're a bit stuck. So that's one challenge. People are getting around that though. Also, synaptic learning rules are very important. How do we change the weights for the synapses if we can't access those synapses? And I think it's fair that we give up that ability if we want to build incredibly dense networks, just like we can't access the synapses of our own brain. And then finally, reconfigurability, which is actually the point that I explained first, and I've confused the 2 points. The first point about converting networks is about how do you convert deep neural networks into spiking neural networks, because they're very different. But thank you very much. I think that's the end of the slide. If you have any questions.
Thanks, Dan and Nitish. Any questions? Maybe.
Person ask a question. It's that at the front.
Okay, sorry, that's how real life things happens.
Okay, so sorry if I missed a bit of the talk earlier on, but in the brain, many of the connections go backwards. So there's a sense that we're interested in the energy of sending stuff forwards. Are there structures where you could either communicate or compute with networks where you're using the knowledge that the later stages know in order to only transmit the new information that tells you the difference between things? That's working.
Yes, so it's just not. I suppose in biological brains, that's driven by sort of sodium backpropagating, backpropagating action potentials. What I understand,
or downward Ethan, is it connections where you've got there's a white mesh back down.
So it is possible because there's some of the more advanced circuits, you can have action potentials that travel from the outputs to the inputs.
Right.
So you can have that backwards feed.
Yeah. Okay.
It's always interesting to play with, but I don't know how you.
Has
create
anyone
models.
looked at whether that makes things more efficient or?
Yes, there are papers that do look into that and see can that improve classification accuracy.
Right.
But I think, yeah, I need to double check those papers as to whether it did help or not.
Right.
Yeah.
Okay.
But it's very big concept. In neuromorphic engineering, it's often like the approach will be, oh, there's actually this thing that we've forgotten about in biology. That's from biology. Let's re-implement that. And so people are always adding in more ions, more propagation mechanics, seeing does it improve the performance.
Right. Okay. No, thanks. Yeah.
Yeah, any other questions? Yeah. Yeah, please, yeah, sorry.
Yes, if we can.
Thank you to both presentations also, but I have a question for Nitish. For the first project that you talked about with the compression transmission for retrieval tests, was there some kind of quantization in the network? Or?
So that's where the input signal is directly mapped to the channel code word in an analog way. So it's not quantized or compressed separately. No, the making it faster was not the purpose of that. Yeah. Yeah. But that could possibly be one further advantage of it, that you don't have separate modules doing the quantization and compression. It's just done in one go. Yeah. Thanks.
Okay, yes, from here in Ors. A question for you. Okay, so yes, I have been working a little bit with neuromorphic computation, and of course, as you mentioned, we have some advantages, also some drawbacks, and those drawbacks are really difficult to overcome, right? So I've also been working with quantum machine learning. Of course, I've been working with quantum neural networks and quantum optimizers. So are you familiar with this concept? Would you be able to draw some relationships between neuromorphic and quantum machine learning? Because once we have quantum computers available for us to work with, I think it will be very promising for us to work with qubits and then to develop those quantum neural networks in a more affordable way. It will be a different approach, of course, but that would contribute to sustainability of AI, of course. So what do you think about this?
But the only thing I would say is that I think they would end up with different application uses because neuromorphic is very much edge processing, whereas quantum machine learning, from what I understand, because of the requirements in terms of temperature and cooling, I doubt so far, yeah. 100 years, who knows? Yeah, but yeah, so I can't comment, I don't think, but beyond the fact that neuromorphic is definitely edge rather than data center kind of applications. Okay.
Like Roger Penrose, the physicist, has this idea of how brain performs computations. So he basically says the brain is doing quantum computations in microtubules. So if somebody picks up that idea and develops it into neuromorphic computing, there might be a connection.
We don't know actually, but we assume that the very quantum level, we could reproduce how the human brain to make things. Because we would based and this computers and also traditional level that we have by this time the traditional level. But of course, it's just every work has to how since at that time we were talking about 5 years from that time to the future. So we are still 5 years to get a quantum computer available for us. Let's keep working.
Well, thanks so much. Thanks, Nitish and Dan. Yeah, and sorry for this disruption.